Introduction. What are you doing, son?
Father, I'm just reading my favorite comic.
Ajay, don't use tap water for drinking purpose. It may be contaminated. Always use RO purifier's water for drinking purpose.
Okay, Father. Father, I want to ask you something about this. How does RO purify work?
Okay, son, I will tell you. It works on the principle of reverse osmosis. The tap water is a solution of water, minerals, metals, or some impurities. RO purifier has a semi-permeable membrane, which allows only water molecules to pass through it, and other molecules cannot pass through the semi-permeable membrane. The tap water acts as a solution and pure water acts as a solvent. The membrane allows only solvent molecules to pass through it.
Okay, Father. Now I get the answer of my question. And I want to know more about this.
Son, to know more about this, you have to study about solutions. Students, today we will study more about solutions. Objectives. At the end of this lesson, you will be able to define vapor pressure, explain Raoult's law, describe Raoult's law for solution of two volatile liquids, differentiate ideal and non-ideal solutions, understand positive and negative deviation, know colligative properties, define osmosis and reverse osmosis, understand abnormal molar masses, and calculate Van Hoff's factor. Vapor pressure of liquid. The pressure exerted by the vapors above the liquid surface in equilibrium with the liquid at a given temperature is called vapor pressure of the liquid. The vapor pressure of a liquid depends on nature of liquid and temperature. Nature of liquid. Liquids which have weak intermolecular forces are volatile and have greater vapor pressure. For example, dimethyl ether has greater vapor pressure than ethyl alcohol. Temperature. Vapor pressure increases with increase in temperature. This is due to the reason that with increase in temperature, more molecules of the liquid can go into vapor phase. The variation of vapor pressure of a liquid with temperature is given by Clausius equation. Here, P1 and P2 are vapor pressures at temperature T1 and T2 respectively, and R is the universal gas constant. Vapor pressure of the solution. When we add a small amount of non-volatile solute to the solvent to form a solution, then the vapor pressure of the solution is only due to solvent. In that case, vapor pressure of the solution is less than that of the pure solvent. In the case of solution, a part of the liquid surface is occupied by solute particles, which are non-volatile. Therefore, evaporation of the liquid will take place from a lesser surface area. This results in lowering of vapor pressure. Raoult's law. The vapor pressure of a solution containing non-volatile solute is directly proportional to the mole fraction of the solvent. In case of solution containing two components, volatile solvent and non-volatile solute, the vapor pressure of solution is given as Pa is equal to K into XA. where K is proportionality constant. For pure liquid, XA is equal to 1. In this case, K becomes equal to vapor pressure of the pure solvent, which is denoted by P, not A. Thus, PA is equal to P naught A into XA. For solutions obeying Raoult's law at all concentrations, its vapor pressure would vary linearly from 0 to the vapor pressure of pure solvent. Raoult's law for solution of two volatile liquids. When two volatile liquids A and B are mixed to form a solution, the vapor phase consists of vapor of both the components of the solution. The partial vapor pressure of each of the component depends on the mole fraction of corresponding component. PA is equal to PA naught into XA, and PB is equal to PB naught into XB. This relationship is called Raoult's law. It states that for a solution of two or more miscible volatile liquids, the partial vapor pressure of each component of the solution at a given temperature is directly proportional to its mole fraction. According to Raoult's law, a plot of PA against XA should give a straight line passing through PA naught when XA is equal to 1. Similarly, a plot of PB against XB is a straight line passing through PB naught when XB is equal to 1. The total vapor pressure, P, exerted by the vapor above the solution is the sum of PA and PB. P is equal to PA plus PB. By putting XA is equal to 1 minus XB, we get the relation P is equal to bracket PB naught minus PA naught bracket close multiplied by XB plus PA naught. Similarly, by putting XB is equal to 1 minus XA, we get the relation P is equal to PA naught minus PB naught whole multiplied by XA plus PB naught. Since PB naught and PA naught are constant at given temperature, therefore, the total pressure P is a linear function of XB or XA. Ideal solutions. A solution is called an ideal solution if it obeys Raoult's law over a wide range of concentration and at specified temperature. For an ideal solution, P is equal to PA plus PB. It can be written as P is equal to PA naught into XA plus PB naught into XB. Liquids having similar nature and structure are likely to form ideal solutions. For example, mixture of methanol and ethanol. Reasons for formation of ideal solutions. A solution of two miscible liquids A and B will be ideal if two essential conditions are fulfilled. If the force of attraction between molecules of A and B is equal to the force of attraction within molecules of A and force of attraction within molecules of B. The solution of A and B liquids will be ideal if A and B have similar structures and polarity. Example on ideal solution. Let's take an example of ideal solutions. Benzene and toluene form a very nearly ideal solution. At 313 Kelvin, the vapor pressure of pure benzene and toluene are 160 mm Hg and 60 mm Hg respectively. Assuming an ideal solution behavior, calculate partial pressure of benzene and toluene, and total vapor pressure of the solution made by mixing 4 mole of toluene and 1 mole of benzene. Let's see the solution. We know that mole fraction of benzene is equal to moles of benzene upon moles of benzene plus moles of toluene whole. On calculating, we get mole fraction of benzene is equal to 0.2 and mole fraction of toluene is 0.8. Now, we calculate the partial pressure and we get partial pressure of benzene is equal to 32 mm of mercury. Similarly, partial pressure of toluene is equal to 48 mm of mercury. Hence, total vapor pressure of solution is equal to 80 mm of mercury. Non-ideal solutions. A solution which does not obey Raoult's law for all concentrations is called a non-ideal solution. Essential conditions for a non-ideal solution are: total volume of the solution should not be equal to volume of solvent A plus volume of solute B. Molecular interaction between the molecules of A, molecules of B, and molecules of A and B are of different magnitude. Therefore, change in enthalpy on mixing A and B will not be zero. Raoult's law is not obeyed. A non-ideal solution can show either positive or negative deviation from Raoult's law. Positive deviation. The deviation will be called positive when the partial pressure of each component and the resultant total pressure are greater than the pressure expected on the basis of Raoult's law. For example, the solution of water ethanol and benzene acetone shows positive deviation. The intermolecular forces between solvent-solute molecules are weaker than those between solvent-solvent and solute-solute molecules. This shows that the vapor pressure of the solution will be higher. Negative deviation. The deviation is called negative deviation if the partial pressure of each component and resultant total vapor pressure are less than the pressure expected on the basis of Raoult's law. For example, the solution of water nitric acid and chloroform acetone shows negative deviation. The intermolecular forces between solvent-solute molecules are stronger than those between solvent-solvent and solute-solute molecules. This shows that the vapor pressure of the solution will be lower. Colligative properties. Those properties of dilute solutions containing a non-volatile solute dissolved in a known amount of a solvent, which depend upon the number of solute particles and not upon their nature, are called colligative properties. The colligative properties of dilute solutions are used to determine the molecular mass of the dissolved substance. The various colligative properties are lowering in vapor pressure, elevation in boiling point, depression in freezing point, and osmotic pressure. Relative lowering in vapor pressure. The addition of a non-volatile solute to a volatile solvent decreases the escaping tendency of the solvent molecules from the surface of solutions, as some of the surface area is occupied by non-volatile solute particles. According to Raoult's law, the relative lowering of vapor pressure is equal to mole fraction of solute. Thus, Pa naught minus P upon Pa naught is equal to Xb, which is equal to Nb upon Na plus Nb. For a dilute solution, Na is much greater than Nb. Hence, neglecting Nb in the denominator, we have
MB is equal to PA naught upon PA naught minus P multiplied by WB into MA upon WA. Elevation in boiling point. Boiling point is the temperature at which the vapor pressure of a liquid becomes equal to the atmospheric pressure. When a non-volatile solute is added to a volatile solvent, the vapor pressure of the solvent decreases. In order to make this solution boil, its vapor pressure must be increased by raising the temperature above the boiling point of the pure solvent. The difference in the boiling point of solution and that of pure solvent is called elevation of boiling point. Elevation of boiling point is denoted by delta Tb, which is equal to Tb minus Tb naught. For dilute solution, the elevation of boiling point is directly proportional to the molar concentration of the solute in the solution. Kb is called molar elevation constant. Molar elevation constant is defined as the elevation in boiling point when 1 mole of a non-volatile solute is dissolved in 1 kilogram of solvent. Depression in freezing point. Freezing point is defined as the temperature at which the vapor pressure of a substance in its liquid phase is equal to its vapor pressure in the solid phase. A solution freezes when its vapor pressure equals the vapor pressure of the pure solid solvent. When a non-volatile solute is added to the solvent, its vapor pressure in the solution decreases. The difference in the freezing point of pure solvent and that of the solution is known as depression in freezing point. Depression in freezing point is denoted by delta Tf, which is equal to Tf naught minus Tf. For dilute solution, depression in freezing is directly proportional to molality of the solution. Kf is called molar depression constant. Molar depression constant is defined as the depression in freezing point when 1 mole of non-volatile solute is dissolved in 1 kilogram of solvent. Osmosis. The passage of solvent from pure solvent or from solution of lower concentration into solution of higher concentration through a semi-permeable membrane is called osmosis. This movement of solvent is only in one direction. Semi-permeable membrane. A membrane through which only solvent molecules can pass, but not the solute ones. For example, cellophane, parchment paper, and wall of living cell. Osmotic pressure. Osmotic pressure is defined as the excess hydrostatic pressure that builds up when the solution is separated from the solvent by a semi-permeable membrane. It is denoted by pi. Osmotic pressure is proportional to molarity of the solution at a given temperature. Pi is equal to CRT. Put the value of C in the equation. We get pi is equal to WB into R into T divided by MB into V. We calculate the value of MB as WB into R into T divided by pi into V. Reverse osmosis. If a pressure larger than the osmotic pressure is applied to the solution side, the pure solvent flows out of the solution through the semi-permeable membrane. In this way, the direction of osmosis is reversed, and so the process is called reverse osmosis. Reverse osmosis is just opposite to the process of osmosis when an extra pressure is applied. Reverse osmosis is used in desalination to get pure water from seawater. Abnormal molar masses. Association. Association of molecules leads to decrease in the number of particles in the solution, results a decrease in the value of colligative property. As colligative property is inversely related to the molecular mass, therefore, higher value is obtained for molecular mass than normal values. Dissociation. Dissociation leads to increase in the number of solute particles in the solution, results increase in the value of colligative property. Since colligative property is inversely related to the molecular mass, therefore, molecular mass of such a substance as calculated from colligative property will be less than its normal value. Van't Hoff's factor. It is defined as the ratio of normal molecular mass to the observed molecular mass of the solute. It is denoted by I. I is equal to normal molecular mass divided by observed molecular mass, or I is equal to observed colligative property divided by calculated value of colligative property. Van't Hoff's factor expresses the extent of association or dissociation of the solute particles in the solutions. In case of association, I is less than 1. In case of dissociation, I is greater than 1. Neither association nor dissociation, I is equal to 1. Did you know? If a saturated solution is heated, the liquid expands, making room for more solute to dissolve. If a saturated solution cools or is left to evaporate, there is less room for solute, so the solute is precipitated. Precipitated solute molecules often link together to form solid crystals. Osmosis is vital to many body processes, including the workings of the kidney and the nerves. Summary. Let us summarize what we have learnt. The pressure exerted by the vapors above the liquid surface in equilibrium with the liquid at a given temperature is called vapor pressure of the liquid. When we add a small amount of non-volatile solute to the solvent to form a solution, then the vapor pressure of the solution decreases. The vapor pressure of a solution containing non-volatile solute is directly proportional to the mole fraction of the solvent. For a solution of two miscible volatile liquids, the partial vapor pressure of each component of the solution is directly proportional to its mole fraction. Liquids having similar nature and structure are likely to form ideal solutions. Boiling point is the temperature at which the vapor pressure of a liquid becomes equal to the atmospheric pressure. Osmotic pressure is the excess hydrostatic pressure that builds up when the solution is separated from the solvent by a semi-permeable membrane. Van't Hoff's factor is defined as the ratio of normal molecular mass to the observed molecular mass of the solute.